All right, this lecture, chapter 19, I'm going to start by going back to the end of chapter 18. So these three chapters, 17, 18, 19, are all about acids and bases. 17 was really about acid and base strength itself, which focused on Ka values. Chapter 18 was really about calculating pH. So there the focus was on concentration of H+. So this slide really contrasts those two things. pH, which was really what chapter 18 was all about. So this was the focus of chapter 18. And then pKa, which is about acid strength, this is the focus of chapter 17. And you want to keep these separate in your mind. So pH is a property of a given solution. It's based on the concentration of H+ in that solution. Okay? So you don't want to say, what is the pH of HCl? Or what is the pH of HNO2? Because pH is a property of a given solution, not of individual molecules. pKa, on the other hand, that's the property of a particular compound. So that's, you have that list of Ka values. Those are properties of those individual compounds. And in lecture 17, we talk about, how that relates to molecular structure. And it's not something that changes with concentration. So it's a property of the molecule itself. All right. Now, the two are related by this equation that's at the bottom. And what I'm going to do first today is actually derive that equation. Because it's really not a new equation. So what we'll be doing in lecture 19 a lot of is talking about the relationship between pH of a solution and the pKa of a given acid in that solution. Okay? So lecture 19 is really going to be a lot about this relationship. So I'll give you a moment if you want to take this down now. It'll just save you from watching lecture 18.3, which wasn't that long, but so the student question is, how is pH a property of an entire solution? Well, pH is the negative log of concentration of H+. So it's about how many moles of H+ there are per liter of that solution. Which you can take any given acid and make a solution of any pH you want using that acid, or at least any pH below 7. So you can take any acid, make a solution with any pH you want. You can take any base and make any solution with any pH you want. So pH is specific to a specific solution, not a general property of that compound. All right? And if you're on the bottom part of copying this, we're going to be writing all that again. So you don't necessarily need to take that all down right now. All right, so I said Chapter 19, we're going to look at specific applications of acid-base equilibrium. And we start with this thing that we call the Henderson-Hasselbalch equation, and I'll do a quick derivation of it. I don't know how Henderson and Hasselbalch got their name on the equation, because really all they did is a very simple mathematical operation. We know the Ka expression for an acid is Ka equals concentration of H plus times concentration of A minus over concentration of HA. So all they did is they rewrote this equation as, okay, Ka equals concentration of H plus times concentration of A minus over HA. It's that the associative property. They applied the associative property. Correct me if I'm wrong. Still the same equation. Then what they did is they took the negative log of each side. So they did negative log of the concentration of, negative log of Ka equals the negative log of concentration of H plus times concentration of A minus over HA. And then just use a property of logs. If I'm taking the log of two things multiplied together, what is that the same as? Taking the log of one plus the log of the other. So, and I get negative log of Ka equals negative log of H plus negative log A minus over HA. Now we have different names for some of these things. Remember when we say negative log of something, how do we abbreviate that? P. So this becomes pKa equals pH minus the log of A minus over HA. So that's one way to write the Henderson-Hasselbalch equation, but they did one last step and just moved the negative log of concentration of A minus over HA to the other side. So the last step is to move this second term to the other side. So if you take out your formula sheets and you look in the equilibrium section, you'll see this equation just written in slightly differently. As pH equals pKa plus the log of concentration of A minus over concentration of HA. So there are some different ways to write it, but say there are some different ways to write it. But we'll use the one on the formula sheet. So this is really just the Ka equation written in a different form and with a couple of long names attached to it. We'll generally just call it the HH equation. But I don't want you to think of it as some new thing. It's just the Ka equation rewritten. Now, what we'll run into in a lot of situations is a special case if we have equal concentrations of an acid and its conjugate base. Then we can say the pH is going to equal the pKa plus the log of, if those two things are equal, what's that ratio? 1. And what's the log of 1? 0. All right. So whenever we run into this situation where we have equal concentrations of an acid and its conjugate base, the pH will equal the pKa of that acid. So remember, the pH, property of the solution, will equal the pKa, property of the given acid. So that relationship is going to allow us, anytime we can manipulate a situation so that we have equal concentrations of acid and conjugate base, it'll allow us to measure the pH of the solution and know that it's equal to the pKa of the acid. All right. So when equal amounts of an acid and its conjugate base are present in solution, then the pH of the solution equals the pKa of the acid. Another way to say that is the concentration of H plus in the solution equals the Ka of the acid. Mathematically, if concentration of H minus A minus equals concentration of HA, then pH equals pKa. Question? Yep. Absolutely. This is, so the student comment is, isn't this just the same thing we could see from the Ka equation? And the answer is yes. The answer is we could have seen this just using the Ka equation. Ka equals concentration of H plus times concentration of A minus over concentration of HA. If these two things are equal, A minus and HA, if those two things are equal, then they're going to cancel out and we can see Ka equals concentration of H plus. So I'm belaboring this point because, you know, a lot of times it's just more convenient to use the logarithmic form of the equation, but it's not a different equation. So anything that we can do using the HH equation, we could also do using the Ka equation because they are the same equation. Question? Student question is, what does P stand for? So P, the reason that we use the letter P, it comes from the word power, because it's 10 to what power equals that thing. So like pH is the power of hydronium ion concentration, and pK is the power of the Ka. 10 to what power? That's where it came from. Oh, Well, if your teacher told you that no one knew where it came from, I guess they were just misinformed. I mean, I like to pretend that pH is named after me, right? Because it is my initials, but. All right, so nothing really complicated there. Let's look at one application, an important one that was brought up by a student a minute ago, and that's an indicator. So an indicator is a compound that changes color when the pH changes. So you can use an indicator to tell you what the pH in a solution is. But any given indicator is only going to have a certain range where it's effective. All right? And so we want to know why there's only a certain range where it's effective, and we want to know, okay, how can we predict where that range will be? All right? So the thing about an indicator, it's usually a weak acid. Let me see. Here, it's usually a weak acid that changes color when it loses H+. That's what an indicator is. It's just a specific kind of acid that if you take the H+ away, it changes to a different color. In other words, its conjugate base is a different color than itself. The structural reasons for that are often very fascinating. And so I'll give you an example here and maybe mention briefly why it is. So methyl orange, a lot of times, I don't want you to get confused. A lot of times the names of indicators have a color in them. And so we might say, oh, a methyl orange solution is red. And that can be confusing because the orange is actually part of the name of the compound. So when I say methyl orange, that doesn't mean the solution is necessarily going to be orange under a certain set of circumstances. So methyl orange is red in its acidic form, but if it loses its proton, it becomes yellow. All right? So what I'm calling H-methyl orange with the hydrogen on, that's red. It loses the hydrogen, becomes yellow. Question? Oh, sorry that the pictures aren't in the notes packets. It's just thought it was extra toner, and since they're black and white, the pictures don't really add much if they're in black and white. Yes, pictures are worth 1,000 words. Maybe I should do these notes and print these notes in color next year. I don't know. So here's the structure of methyl orange. All right, with the hydrogen on here, it's red. Lots of indicators have structures like this with lots of delocalized pi bonding. You remember us talking about delocalized pi bonding in the beginning of the year. Turns out that delocalized pi bonding a lot of times allows compounds to absorb visible light, so they have a color. When you pull the hydrogen off, when this loses the H+ from the middle here, notice the delocalized pi bonding is actually extended through more of the molecule than it was before. And that's what results in the change in the light absorbance, which results in the change in color. So lots of indicators, if you look up their structures, are going to have structures similar to this. So here's the equilibrium we're dealing with. To make our lives easier, rather than writing out this formula every time, we will call this red one, here, why don't I match the color? We'll call this red one HIN, standing for H indicator. The IN there is not standing for indium, the element IN. And then we'll call the yellow one IN minus. Right, so it's like HA and A minus. So it's red if it has the proton on. If it takes off its proton, it turns yellow. All right. So here's what I want you to imagine. well, first of all, I'll tell you the pKa of methyl orange is 3.8. So imagine a situation where we put methyl orange in a solution, and the solution has a pH of 2.8. Now in that solution, am I going to have more yellow fish or more red fish? So the pH is 2.8. Well, here's my equation. We're considering this equilibrium. We have the indicator and its conjugate base. Apply the Henderson-Hasselbalch equation. All right. pH equals pKa. What I did here, pH, I just moved the pKa to the other side. So I did pH minus pKa equals that, the log of that ratio. So if the pH is 2.8, the pH is lower than the pKa, that is going to be -1. How do I undo the logarithm? I put it into an exponent. So now that ratio itself is going to be 10 to the -1, or 1/10. So which do I have more of in the solution then? Red rubber duckies or yellow rubber duckies? Red, by a factor of 10 to 1, right? So if you zoom out and you're looking at the solution, what are you going to see? Red. So at a pH of 2.8, there's going to be 10 times more red molecules than yellow molecules. You look at the solution, what you'll see is red. If I bump the solution up to the pH of the solution up to 3.8, so the pH equals the pKa. What do we know when pH equals pKa? Concentrations of acid and conjugate base are equal. So now I'm going to be zooming out. I'm looking at a closet that's half filled with, I guess this doesn't work because the red shoes and the yellow boots are different sizes. Well, let's say they were duckies, red duckies and yellow duckies. If I zoom out and I have half red duckies and half yellow duckies, what am I going to see? Orange. So at a pH of 3.8, it's going to appear orange. If I bump the pH up to 4.8, now I have the war between the mustard men and the ketchup men. Now, 4.8 minus 3.8 is +1. So if that logarithm is +1, the ratio is 10 yellows for every 1 red. So now at a pH of 4.8, what color am I going to see? I'm going to see yellow. I'm going to see the mustard. All right. So what's the takeaway? There's going to be a change in color that appears right around a pH of 3.8. So right around 3.8, this will appear orange. But if you go a little lower, it's going to be red and stay red. If you go a little higher, it's going to be yellow and stay yellow. So really, this is going to have an effective range where it's changing color of about 1 pH unit on either side of the pKa. All right. So in general, the color of an indicator will change within about 1 pH unit of its pKa. All right, that's our time for today. We can tie up any loose ends on that tomorrow or Monday.